At 10:49 on the morning of April 28th, a small pool of near-boiling water inside a closed-off corner of Yellowstone National Park exploded. There were no tourists nearby. There hadn't been in almost 2 years, because the boardwalk that used to run past the pool was torn out in the summer of 2024 after a much larger explosion at the same exact spot threw rocks at the people standing there. The only witness on April 28th was a webcam mounted on a remnant of that destroyed boardwalk, and what the webcam saw was the 5th explosion at that same pool in 2026. 5 events, 5 months, 1 pool. Black Diamond Pool in Biscuit Basin has now had the highest documented frequency of explosive activity of any single named feature in the entire modern, instrumented record of Yellowstone, and it is telling us something the public has been refusing to hear for 40 years. Because the dangerous thing about Yellowstone on every timescale that matters to a human being is not the supervolcano, it is something else, and almost no one in North America has been told what it is. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1, April 28th, at 10:49. At 10:49 on the morning of April 28th, 2026, a small pool of near-boiling water inside a closed-off corner of Yellowstone National Park exploded. There were no tourists nearby. There hadn't been tourists nearby for almost 2 years. The boardwalk that used to run past the pool was gone, torn out and relocated after a much larger explosion at the same pool in the summer of 2024. The only witness to the April 28th event was a webcam mounted on a remnant of that destroyed boardwalk, watching the water with the kind of patience only a machine can sustain. And what that webcam saw was a column of brown and grey rising suddenly from the pool's surface, rocks and mud lifting clear of the water, the entire feature for a few seconds blurring into a churn of vapour and debris, and then, almost as quickly as it began, the column collapsing back into the basin and the pool refilling from the same hot spring feed that had been quietly delivering water to that same hole in the ground for as long as anyone has been keeping track. It was the 5th time that exact pool had exploded in 2026, and we are not even halfway through the year. The pool is called Black Diamond Pool. The basin it sits inside is called Biscuit Basin. The webcam is one piece of a sensor network that did not exist 3 years ago, and the 5 events of 2026 are, taken together, the highest documented frequency of explosive activity at that single named feature in the entire modern instrumented record of Yellowstone National Park. The April 28th event is the first of those 5 that the new webcam caught on a clear enough morning to actually see. The first 3 happened at night, or when the camera lens was iced over, or both. The 4th happened under conditions where visibility was marginal, and the explosion may have been laterally directed at low angle, which is a phrase that means very different things from a vertical eruption. The April 28th event is the one we have direct video of, which is why today you're looking at a screen with that footage on it, and you're going to spend the next 2 hours understanding exactly what you are looking at, and why the thing you are looking at has been telling us for almost 2 years now that the public has been worried about the wrong thing at Yellowstone, because here is the part that the news cycle has never quite been able to land on. The dangerous thing about Yellowstone on every timescale that matters to anyone watching this video is not the magma chamber. The dangerous thing about Yellowstone is not the supervolcano. The dangerous thing about Yellowstone is a category of event that has happened thousands of times in the geological history of the caldera, that happens regularly in the present, that has a name most people have never heard, and that produces, every few years, an event almost exactly like the one Black Diamond Pool just had 5 of. The name of that category is hydrothermal explosion, and the reason it matters, the reason it is the actual story rather than the imagined one, is that hydrothermal explosions occur on no warning, in places where people are sometimes standing, with energies sufficient to kill at close range. The next moderate one will happen. The question is not whether it will happen. The question is whether tourists will be standing in front of it when it does. That is the central question of this entire video. Hold on to it. We're going to spend 2 hours building the case for why that question is the right one to be asking, and why the question you have probably been asked to ask, when will Yellowstone erupt as a supervolcano, is, on every timescale relevant to a human life, the wrong question. We're going to do this by spending most of the time on one specific pool, one specific basin, one specific date in April. Because the small story is the way into the large one. The fifth event at Black Diamond Pool, captured at 10:49 on a clear Tuesday morning, is the lens. Everything else in this video is what becomes visible when you look through it. So let's stay with the April 28th event for a moment longer. The webcam captured the moment of explosion in real time, at standard video frame rate, from an elevation about 3 meters above the pool's surface, looking obliquely across the water. The footage runs for approximately 12 seconds, from the moment of first surface disturbance to the moment the column collapses. What you see in those 12 seconds is, first, a brief flat shudder across the water's surface, which is the seismic energy from beneath the pool reaching the surface a fraction of a second before the actual ejection. Then you see the surface lift. The lift is not centered on a single point. It rises across an arc roughly 2 meters wide on the pool's eastern side, where the conduit beneath the pool is now understood to be most active following the structural changes of the 2024 event. The lift develops, in the span of about 2 seconds, into a vertical column. The column reaches a height of approximately 15 meters above the pool's surface at its peak, which the YVO researchers know precisely because the webcam's frame includes calibration markers placed at known heights against the basin's back wall. The column contains liquid water that has been entrained from the pool, mud and clay from the conduit walls and from the pool floor, and rock fragments ranging from gravel to small cobbles. Some of those rocks travel beyond the pool's immediate margin. None of them travel far enough to reach the relocated boardwalk, which was the engineering goal of the post-2024 relocation. Then, over the next 4 to 5 seconds, the column collapses. The entrained water falls back into the pool and onto the surrounding sinter apron, and the steam dissipates into the cooler air above the basin. Within minutes, the pool begins to refill from the same hydrothermal feed that supplies it continuously. Within an hour, the pool is back to a surface that, to a casual observer, looks unchanged. The fish-eye view of geology, which is the view that watches over months and years, would notice that the pool's vent geometry has been further modified, that the eastern side of the conduit is now slightly wider than it was the day before, that the temperature profile measured by the YVO thermistor has shifted by a small but measurable amount, and that the dissolved gas concentrations have changed in a way consistent with disturbance of the shallow plumbing. But the eye that watches over hours and days would see, by sundown on April 28th, a pool that looks more or less the same as it did at sunrise. That is the kind of event a hydrothermal explosion is, on the small end. It is over in seconds. It modifies the system in ways that only the instruments can resolve. It does not announce itself afterwards. It just happens, and then it stops happening, and then the system continues. What makes the April 28th event the one we will keep returning to is not its size. It was not large. It was by every measure one of the smaller events of the 2026 sequence. What makes it the focal point is that it is the one we can actually see, which means it is the one against which we can calibrate everything else. The other 4 events of 2026 are reconstructed events, in a sense. They are known to have occurred because the seismic and infrasound sensors registered them, because the water level pressure transducer recorded the sudden drop and refill, because the post-event surface examination found ejected debris distributed in patterns consistent with explosions of particular sizes and directions. But none of them produced a clean visual record. The April 28th event did. And so when YVO publishes its analyses of the 2026 sequence, which it is doing now in real time in updates that appear on its public communications channels, the April 28th event is the reference. The other 4 are described in terms of how they compare to that one, and so we begin there. Because if you understand what April 28th at 10:49 looked like, and what it sounded like inside the basin, and what it meant in the records of the sensor network that surrounded it, then you are most of the way to understanding what hydrothermal explosions at Yellowstone are, why they matter, and why the small pool that produced this one is now telling us something the larger story has been trying to tell us for years. Whether anyone is listening, of course, is a separate question. It is a question the rest of this video will spend time with. But first, we need to go back about 21 months, to a sunny Tuesday morning in July of 2024, when a much larger version of the April 28th event happened in front of about 200 tourists with phones in their hands, because that event is the one that put Black Diamond Pool on the map, that drove the construction of the monitoring network whose data we are now reading, and that, more than any other single moment in the recent history of Yellowstone, changed what the American public knows about the way this park can hurt them. Part 2. The July 2024 explosion that started all this. There is a particular kind of footage that exists only because someone happened to be holding a phone at the right moment. The July 23, 2024 hydrothermal explosion at Black Diamond Pool is that kind of footage. By the time the rocks started landing on the boardwalk, more than a dozen tourists had their cameras pointed at the pool. By the time the dust settled, that number was closer to 50. By the time the videos had been uploaded to social media, edited together, and pushed through the algorithmic engines of every major platform, the term hydrothermal explosion had crossed from a phrase confined to volcanology journals into a phrase that ordinary people typed into search bars at home, in cars, on the subway, in line at coffee shops. It became, briefly, one of the most searched terms in the geological sciences, and the reason it broke into the public vocabulary was not because someone gave a particularly compelling lecture on it. It was because, on a clear Tuesday morning in July, at 5 minutes before 10, a hole in the ground produced an event that looked, to a human eye standing 40 feet away, like the world was opening up. The event happened at 9:55 in the morning Mountain Time. The day was clear and warm. Biscuit Basin had its usual morning crowd, which is to say a few hundred people scattered across the basin's two boardwalks, with most of them gathered near Sapphire Pool and Jewel Geyser at the basin's main feature complex. Black Diamond Pool sits a bit apart from those features, on a separate spur of boardwalk that loops around the western side of the basin. Black Diamond Pool, in 2024, was a pool that most visitors didn't pay particular attention to. It was a roughly circular feature about 10 meters across, with deep blue-green water, a continuous low-volume gas emission that produced a slight surface ripple and a sinter apron extending a few meters from its margins. It looked, to a tourist who had walked the basin trail dozens of feature-rich meters past Sapphire Pool's spectacular blue water, like a smaller and less impressive version of the basin's named attractions. People generally walked past it. On the morning of July 23rd, the people on the boardwalk near Black Diamond Pool were the people who had paused there for a moment longer than usual, perhaps because they had been reading the interpretive sign, perhaps because someone in their group needed to rest, perhaps because the morning light was particularly good for photographs. The first sign anyone had that something was wrong was a low rumble. It was not loud. People described it later as a hum, as a vibration in the boardwalk, as a sound that they felt in their feet before they heard it in their ears. It lasted about 2 seconds. Then the pool's surface heaved upward. The heave was unmistakable. The water rose in an instant by perhaps 2 meters, lifting in a domed shape that was, to the tourists watching it, immediately and obviously something they should not be standing close to. People started running. Some of them dropped their phones. Some of them kept filming as they ran. The rise of the dome over Black Diamond Pool, the moment the dome ruptured into a column of brown and grey, the moment rocks began to fall on the boardwalk and onto the sinter apron, all of it is preserved in dozens of overlapping clips taken from dozens of angles, by people who were running in different directions while their cameras kept recording. The column itself reached an estimated height of about 30 to 40 meters above the pool's surface at its peak. The total event lasted about 30 seconds from first surface disturbance to final collapse of the column. During those 30 seconds, the pool ejected an estimated 300 to 500 cubic meters of material in total: superheated water, mud, clay, and rock. The largest rocks ejected were on the order of 20 to 30 centimeters across. Several of those rocks landed on the boardwalk. One of them broke a boardwalk plank. 2 of them landed within 5 meters of where tourists had been standing seconds earlier. No one was directly struck. No one was killed. No one was even seriously injured in the immediate event, though several people had minor injuries from the running and falling that followed. By any reasonable standard, the National Park Service and the YVO researchers who later assessed the event agreed that the absence of fatalities was a function of pure geometry. The rocks went where they went, the people stood where they stood, and the 2 paths did not intersect. What the rocks did do, though, was damage the boardwalk. The boardwalk section closest to Black Diamond Pool was destroyed in several places. The interpretive signage was thrown clear. The walking surface was no longer safe to use. By the end of the day, the National Park Service had closed Biscuit Basin to the public. By the end of the week, the NPS had announced that the basin would remain closed until further notice, that the boardwalk infrastructure would be reviewed and likely relocated, and that USGS would be working with the Park Service to install additional monitoring at the pool itself. What unfolded over the next 21 months is what built the sensor network whose data we are reading right now. YVO worked with NPS and with several research universities to install, around Black Diamond Pool, a level of monitoring that exceeds what most other features in the park have ever had. A new webcam, mounted on a stable remnant of the destroyed boardwalk, gave a continuous visual feed. A seismometer placed within meters of the pool gave a record of shallow seismic activity that the broader park network could not resolve from kilometers away. An infrasound microphone array gave a way to localize the energy and the directionality of any future explosion. A pool water level pressure transducer, dropped into the water itself, gave a continuous record of fluctuations in the pool's depth. A pool temperature thermistor gave continuous temperature data, and, added in mid-2025, a continuous dissolved gas sampling line that drew small water samples from a specific depth in the pool and analysed them automatically for the gases that the volcanology literature has linked to disturbance of shallow hydrothermal systems. The boardwalk was relocated. The new boardwalk, which is the one closed to the public today, sits about 30 metres farther from the pool than the original. The viewing angle is different. The pool is still visible from the new boardwalk's perimeter, but the relocation creates a safety buffer that, in the assessment of the engineering review, would protect tourists from the kind of debris ejection pattern observed on July 23rd. The boardwalk has been closed to public access since the event, pending YVO's assessment that the pool has stabilised. As of May 2026, YVO has not made that assessment. The pool has not stabilised. The 5 events of 2026 are the evidence of that. YVO's published analysis of the July 23rd event, which appeared in a peer-reviewed paper in early 2025 and in several USGS bulletin updates in the months between, settled on a mechanism that is now the standard interpretation. The trigger was not a deep magmatic event. The trigger was not an earthquake elsewhere in the park. The trigger was a self-sealing, self-pressurizing cycle local to the conduit beneath the pool. Over a period of months to years before the event, mineral precipitation along the conduit walls had been progressively narrowing the throat of the system through which hot water rose to the pool. As the throat narrowed, the pressure of the water and steam mixture in the deeper conduit increased. The water beneath the seal was at a temperature high enough that it would have flashed to steam at lower pressure, but the pressure was holding it as liquid. When the seal failed, when the pressure inside the conduit finally exceeded the strength of the mineral and the weight of the overlying water, the trapped water flashed instantly to steam. The volumetric expansion of that flash, at the temperatures and pressures involved, was on the order of a factor of 1,600. That expansion is what drove the ejection. It is what lifted the dome of water. It is what threw the rocks. It is what produced the column of vapour and debris that reached 30 to 40 metres into the air above the basin floor. Everything else in this video, and everything else in the modern story of Yellowstone's hydrothermal hazard, follows from that mechanism. So before we go further into what the 2026 sequence looks like, what the basin around Black Diamond Pool is, and what the actual hazard ranking of Yellowstone says about all of this, we need to spend a few minutes inside that mechanism, because the entire reason hydrothermal explosions are a real and recurring threat at Yellowstone is rooted in physics that is, at its core, almost embarrassingly simple. Hot water that wants to be steam, held under pressure by a seal, sees its seal fail and becomes steam in an instant. Multiply that by the depth and the temperature and the conduit size of any of Yellowstone's 10,000 features, and you have, as a baseline state of the park, a system that is geologically guaranteed to produce events like the one you just watched on the April 28th webcam footage. The only question, ever, is which feature, and how big, and when. Part 3. How a hydrothermal explosion actually works. Imagine that you are looking at a column of water about a kilometre tall, not in a glass, in the ground, or more precisely in the cracks and pore spaces and conduits and reservoirs of the rock beneath a place like Biscuit Basin. At the top of the column near the surface, the water is at atmospheric pressure and is bubbling and steaming and venting into the air as the spring or pool that you can see. At the bottom of the column, a kilometre down, the water is at the pressure of a kilometre of overlying rock and water, which is somewhere in the range of 200 to 300 atmospheres. Pressure in a fluid column increases roughly linearly with depth, so somewhere in the middle the pressure is intermediate. Now consider the temperature. The water at the surface is at some temperature in the range of perhaps 90 degrees Celsius for a pool that is actively boiling. The water at the bottom of the column, deep where the rock has been heated by the magma chamber, another 4 to 9 kilometers down, is at a temperature on the order of 250 to 350 degrees Celsius. So temperature, like pressure, increases with depth. And here is the key part, the part that the geology of Yellowstone is built on. The pressure-temperature relationship of water is such that, at the deep conditions of the column, the water is hot enough that it would, if held at atmospheric pressure, instantly become steam. But it is not at atmospheric pressure. It is at 200 or 300 atmospheres, and at that pressure, the water remains a liquid even at 350 degrees. It is, in the technical phrase, superheated. It is liquid only because the pressure is holding it as liquid. As the water rises up the column toward the surface, the pressure decreases. At some depth, exactly which depth depends on the temperature and the chemistry, the water reaches the point where its temperature corresponds to the boiling pressure for that temperature, and from that depth upward, the water begins to boil, not all at once. Boiling, in this kind of system, is a gradual, continuous process that happens across a thickness of meters to tens of meters. As the water boils, it transitions from a liquid phase to a two-phase mixture of liquid water and steam. The mixture continues to rise. As it rises, more of it transitions to steam, until, near the surface, the mixture is mostly steam, with some entrained droplets of water, which is what you see escaping from a fumarole or what makes the surface of a hot spring shimmer. That is the baseline behavior of a thermal feature at Yellowstone. The system finds its steady state. The water rises and boils and vents, and the surface expression is a hot spring, or a geyser, or a fumarole, depending on the geometry of the conduit and the rate at which water is supplied from below. Now consider what mineral precipitation does to this system. The water in the deep conduits at Yellowstone carries dissolved silica, dissolved chloride, dissolved bicarbonate, dissolved sulfate, and various other species in solution. When water at high temperature comes into contact with rock at high temperature, the rock dissolves into the water at a rate that depends on the temperature and the chemistry. The water that emerges in a pool like Black Diamond Pool is therefore not pure water. It is a chemically loaded brine, in essence, that has been picking up dissolved species during its journey upward. As the water cools and depressurizes near the surface, some of those dissolved species become less soluble, and they precipitate out of solution. Silica, in particular, precipitates as the water cools and as the pressure drops below the saturation curve. The result is a continuous, slow process of mineral deposition in the conduit. Layer by layer, micrometer by micrometer, year by year, the inner walls of the conduit accumulate silica and other minerals. The conduit narrows. Now what happens as the conduit narrows? In a steady-state geyser, the system adjusts. The water rises more slowly through the narrower throat, and the eruption cycle changes, but the system remains balanced. In a pool, though, where the surface expression is a quiet pool rather than an episodic eruption, the narrowing of the conduit beneath the pool can produce a different outcome. The depth at which boiling begins moves upward as the throat narrows, because the increased flow resistance changes the pressure profile in the column. The two-phase region, the region where water and steam coexist, moves upward toward the pool. The pressure in the deep conduit, beneath the constricted throat, can rise. The water beneath the constriction can become more deeply superheated than the long-term equilibrium would normally allow. This is the seal and pressure mechanism. The conduit walls themselves, by precipitating minerals, become a slow-acting seal at the top of a region of high-pressure, high-temperature water. The seal is not perfect. Water continues to flow through it, but the seal is significant. And the water beneath the seal carries, by virtue of the depth and the temperature, enough internal energy that if the seal were to suddenly fail, the water would flash to steam instantly. The volumetric expansion of liquid water to steam at typical Yellowstone deep system conditions is on the order of a factor of 1,600. That is a number worth pausing on. 1 cubic meter of superheated liquid water at 300 degrees Celsius becomes, when the pressure is released and the water flashes to steam at atmospheric pressure, approximately 1,600 cubic meters of steam. Multiply that across the volume of water that is trapped beneath a self-sealed conduit, and you have, in an instant, a volume of steam thousands of times larger than the original water volume expanding outward into a confined space. The expansion drives everything above it upward. The water that was sitting in the pool above the conduit is lifted. The rocks and mud and sediment in the conduit are entrained in the expansion and ejected upward with the steam. The result is the column of vapour and debris that the webcam recorded on April 28th, and that the tourist phones recorded on July 23rd. Once the steam has expanded and the pressure is released, the system returns to a lower energy state. The conduit, which was sealed, is now open temporarily, because the explosion has cleared material from inside it. The pool, which had been sitting at a stable level, has been disturbed and is refilling from the deeper feed. Over the next hours and days, the conduit walls begin to precipitate minerals again. The seal begins to reform. The cycle, in principle, begins again. This is the canonical mechanism. It does not require new magma. It does not require a deep system change. It does not require an earthquake to trigger it. It requires only the standard background heat of the Yellowstone hydrothermal system, the standard background chemistry of the water, and the standard background process of mineral precipitation. Given those conditions, hydrothermal explosions are not a special event that happens occasionally for unusual reasons. They are an ordinary consequence of the way the system works. They are the way the system periodically resets itself, and they happen, across the park, at a baseline rate that is significant on a human timescale, even though it is geologically modest. What controls the size of an individual hydrothermal explosion is, primarily, the volume of water that has been sealed beneath the conduit and the depth at which it was sealed. A small seal at shallow depth produces a small event, a brief low-column, modest debris ejection, the kind of thing the April 28th event was. A large seal at moderate depth produces a pork-chop-scale event. Ejection tens of meters, surface modification of the feature, the kind of thing that occurred at Norris Geyser Basin in 1989. A very large seal at substantial depth produces something on the scale of the prehistoric Mary Bay event. A crater 2.5 kilometers across, ejected blocks travelling kilometers from the source, an event geologically rare but absolutely on the menu of what this system can produce. The size distribution of hydrothermal explosions at Yellowstone, taken across the geological record, follows a frequency-magnitude relationship similar in shape to the one earthquakes follow. There are many small events. There are few large ones, and the rate of any particular size class is approximately a power law function of the size. Small events happen multiple times a year somewhere in the park. Medium events happen every few years. Large events happen every few centuries. The largest documented events happen every few thousand years. This is the system you are looking at when you watch the April 28th footage. You're watching a small expression of an enormous, ongoing geophysical process that the entire surface of Biscuit Basin and Norris Geyser Basin and the Upper Geyser Basin and every other thermal area in Yellowstone is a manifestation of. The system is doing what it does. The April 28th event is the system doing what it does, 15 meters in the air, at 10:49 in the morning, on a closed-off boardwalk in front of a webcam mounted on the remnant of an older boardwalk. The system does not care that we are watching. The system has been doing this for hundreds of thousands of years. What is new in 2026 is that we are watching with enough instrumentation to see it for what it actually is. Whether we understand what we are seeing is a separate question. That question is what the rest of this video is about. Part 4. Why 5 explosions in 5 months is the anomaly. So if hydrothermal explosions are the normal, ongoing baseline of a place like Yellowstone, then the question that anyone with even a basic instinct for statistics should be asking by now is this: what makes the 2026 sequence at Black Diamond Pool an anomaly at all? If the system produces these events constantly all across the park, then why does 5 at one pool over 5 months stand out? The answer is in the rate, and in where the rate sits relative to the baseline at that specific feature. In 2024, before the July 23rd event, Black Diamond Pool was not on YVO's list of high-frequency hydrothermal explosion sources. It was a quiet pool. Its observed rate of explosive activity, in the years for which records exist, was on the order of one detectable event every several years to perhaps once a decade, depending on how broadly you define detectable. The July 23rd event was the first event of consequence at Black Diamond Pool in years. The rest of 2024 after the July event produced 2 more small events at the same pool, both of them in the months immediately following, both of them small enough that they would have been missed entirely without the new instrumentation. 3 events in the second half of 2024 then. In 2025, the pool was quieter. There were perhaps 2 events, both small, both detected by the sensor network, but not large enough to be widely reported. Then 2026 began, and by the end of April, the pool had produced 5 events. 5 events in 5 months. That number is approximately 10 times the historical pre-2024 rate for the same feature, and it is more than twice the rate seen in the 2025 recovery year. Even compared to the second half of 2024, when the system was still ringing from the July event, the 2026 rate is substantially higher. What does that elevation mean? There are, in the published volcanology literature and in YVO's own communications, 4 interpretations that get applied to a sequence like this, and they are not mutually exclusive. The honest answer to what is going on at Black Diamond Pool is some weighted mix of all 4. We will go through them in order, because each of them has different implications for what comes next. The first interpretation, and the one that the data most strongly supports, is the conduit modification hypothesis. The July 2024 event physically modified the conduit beneath Black Diamond Pool. The explosion cleared some material from inside the conduit. It changed the shape of the throat through which water rises. It exposed new mineral surfaces to the hot, mineral-saturated water. New mineral surfaces, all else equal, drive faster mineral precipitation, because the precipitation reaction is surface-controlled. The more surface area available, the faster the deposition. Faster deposition means faster resealing, and the new conduit geometry, having been carved by an explosion rather than slowly equilibrated, is by definition farther from its long-term equilibrium shape than it was before. A conduit that is out of equilibrium will, in a hot mineral-saturated fluid system, evolve toward equilibrium through some combination of dissolution, precipitation, and mechanical erosion. The rate of that evolution can be elevated for years, even decades, after a major perturbation. Under the conduit modification interpretation, the 2026 sequence is a delayed onset consequence of the 2024 event. It is the system finding its new equilibrium. It is local to Black Diamond Pool. It is mechanistically isolated from anything happening elsewhere in the park, and it should be expected to gradually decay over months to years as the conduit walls stabilize. The second interpretation is the basin reorganization hypothesis. Hydrothermal systems are interconnected at scales that are not always obvious from the surface. The features of Biscuit Basin, Sapphire Pool, Jewel Geyser, Black Pearl Geyser, Black Diamond Pool, and the smaller named and unnamed features share, at some depth, fluid pathways. Disturbance in one part of the shallow plumbing can propagate to other features over time. If the basin as a whole is undergoing a low-grade reorganization of its shallow plumbing, perhaps as a delayed consequence of the 2024 event, perhaps for reasons unrelated, then Black Diamond Pool's elevated activity may be the most visible symptom, but not the only one. Other features in the basin would, under this interpretation, be expected to show subtle anomalies. As of May 2026, YVO's public communications have not described detectable anomalies at other Biscuit Basin features, but the basin reorganization interpretation cannot be ruled out, because the sensor coverage at the other features is less dense than at Black Diamond Pool, and the analysis is ongoing. The third interpretation, which is the one that drives most of the speculative public discussion, is the precursor hypothesis. Under this framing, the elevated rate at Black Diamond Pool is a precursor to a larger event, either at Black Diamond Pool itself, scaled up, or somewhere else in the basin or the park. The historical record of larger hydrothermal explosions, the ones in the Pork Chop or Mary Bay size class, does not consistently support a precursor pattern of small events at the same feature in the months and years before the big one. The July 2024 event was not preceded by an obvious small event precursor sequence. The prehistoric Mary Bay event left no documented precursor record because there was no instrumentation to record one. So the precursor hypothesis, while it cannot be definitively ruled out, has the weakest empirical support of the 4 interpretations. The data does not show a consistent pattern by which small explosions reliably foreshadow larger ones. They may, in some cases, but the relationship is not predictive enough to function as a warning. The fourth interpretation, and one that is straightforwardly correct as a partial contribution to the apparent rate, is the detection improvement hypothesis. the instrumentation around Black Diamond Pool after July 2024 became substantially better than what existed before. A small explosion that would have gone entirely undetected in 2023, happening at night, under ice cover, with no boardwalk-adjacent witnesses, would in 2026 be clearly recorded by the seismometer, the infrasound array, and the pool-level pressure transducer, even if the webcam saw nothing. The apparent rate at Black Diamond Pool in 2026 therefore reflects, in part, the system's ability to count smaller events that, in earlier years, would not have been counted. Some unknown fraction of the elevation above the historical rate is therefore a detection effect, not a real activity increase. YVO's own communications acknowledge this caveat. Determining what fraction is real elevation versus detection improvement requires more analytical work than has yet been published. There is also a fifth consideration that does not rise to the level of a competing interpretation, but that deserves a brief mention because it is part of the honest picture. The Yellowstone hydrothermal system is, like all natural systems, subject to genuine stochastic variability. The arrival rate of events at a given feature is not constant. It fluctuates around some mean rate, and the fluctuations themselves are part of the system's normal behavior. A cluster of 5 events in 5 months, against a background mean of perhaps 1 event every couple of years at that feature, is unusual but not necessarily statistically impossible by chance alone. The Poisson distribution that describes random event arrival times allows for clusters at rates much higher than the long-term mean, simply because random arrivals are not evenly spaced. Some of the apparent elevation at Black Diamond Pool may be a true increase in the underlying rate. Some of it may be a chance fluctuation around an unchanged rate. Disentangling the two requires more data than we currently have, which is one of the reasons the sensor network continues to record. Every additional event adds a data point that helps separate the chance fluctuation contribution from the genuine rate increase. So which of these is the right answer? The honest answer is that it is some weighted combination of all of them, with the conduit modification interpretation almost certainly being the largest contributor. The basin reorganization interpretation likely contributing some, the detection improvement effect contributing some, the stochastic variability contributing some, and the precursor interpretation contributing little to nothing. The trajectory implied by that combination is the one YVO is publicly working from. The trajectory is continued small events at Black Diamond Pool over the coming months to years, with gradual stabilization as the conduit reaches a new equilibrium, with no expected escalation to a larger event at Black Diamond Pool, with no expected propagation to the rest of Biscuit Basin, and with continued closure of the basin to the public as a precaution against the small but non-zero residual risk that some larger event does occur. That is the assessment. It is grounded in the data. It is consistent with the published volcanology of hydrothermal systems. And it is, importantly, the assessment that the entire monitoring network around Black Diamond Pool was built to test. The reason we have a webcam pointed at that pool, a seismometer in that basin, an infrasound array on that boardwalk remnant, and a dissolved gas sampler in that water is so that if the trajectory shifts, if YVO's interpretation turns out to be wrong, if the basin reorganization scenario starts producing detectable anomalies at other features, if the precursor scenario becomes the right model, the sensor network will see it before the public sees it. That is the entire point of the instrumentation. The point is not to confirm what we already think. The point is to detect a deviation from what we already think, and to give us enough warning that the consequences of being wrong can be mitigated. What that whole picture lands on is a sentence that the rest of this video will keep returning to. The 2026 sequence at Black Diamond Pool is not, by itself, a precursor to anything dramatic. It is instead the system showing us, in real time, the category of event that the public's mental model of Yellowstone has been ignoring for decades. And the question of what is actually dangerous about Yellowstone, the real Yellowstone threat, the one in the title of this video, does not start with the magma chamber. It starts here, with a small pool that has now exploded 5 times in 5 months. To understand why the public has the threat profile backwards, we have to look at what USGS itself says about the hazard ranking of the entire park. Because what USGS says and what the public thinks are not the same thing, and the gap between them is, in a quiet way, one of the more consequential failures of science communication in the modern history of American geological hazards. Part 5. USGS's actual hazard ranking. If you sit down today, in 2026, and you read the official United States Geological Survey assessment of hazards at Yellowstone National Park, you will encounter a document that, if you have spent most of your adult life consuming popular media about Yellowstone, may be a little surprising to read. The document in question is the most current iteration of the hazard framework that originated with the Christensen et al. Assessment of 2007 and has been updated through subsequent USGS bulletins, the most recent of which incorporates the data through the post-2024 monitoring upgrades. The document does several things. It enumerates the categories of hazardous events that can occur at Yellowstone. It ranks them by relative likelihood over a human-relevant timescale, and it estimates the consequences of each category if it were to occur. The ranking from most likely to least likely goes like this. First, large earthquakes. Not because Yellowstone is a uniquely earthquake-prone region, but because the park sits inside the broader intermountain seismic belt, and because the historical record includes the 1959 Hebgen Lake event, a magnitude 7.3 earthquake that, while its epicenter sat just outside the caldera proper, was very much a Yellowstone region event by every meaningful criterion. The annual probability of a magnitude 7 or greater earthquake somewhere in or near the caldera, based on the historical record and on the active fault mapping, is on the order of 1 in several hundred years. That is the most likely category of hazardous event at Yellowstone. Second, hydrothermal explosions. This is the category we have been discussing. Annual probability of a pork chop scale or larger hydrothermal explosion somewhere in the park is on the order of 1 in a few decades. That is roughly an order of magnitude higher annual probability than a caldera-forming eruption. It is several orders of magnitude higher annual probability than a caldera-forming eruption when you weight by consequence. Because while caldera-forming eruptions would be catastrophic on a continental scale, hydrothermal explosions, even moderate ones, can be lethal at close range and modify the surface geometry of the park in ways that affect the visitor experience indefinitely. Third, lava flows. Yellowstone has produced lava flows in its post-caldera history, the most recent in the geological record being on the order of 70,000 years ago. Lava flows are slow, they are not particularly dangerous to anyone with a working pair of legs, and they would, in the modern Yellowstone, primarily affect the park's infrastructure rather than visitors directly. Annual probability of a lava flow event is roughly 1 in 100,000 or so years, integrated across all possible vent locations. Fourth, small to moderate explosive eruptions. These are eruptions that involve magma reaching the surface and producing explosive activity, but at a scale much smaller than a caldera-forming event. Yellowstone has had small explosive eruptions in its post-caldera history. They are rarer than lava flows. Annual probability is on the order of 1 in several 100,000 years. Fifth, and last, caldera-forming super-eruptions. Annual probability is on the order of 1 in 700,000 years. This is the category the public's mental model treats as the dominant Yellowstone hazard. It is, in the actual hazard ranking, the least likely category by a wide margin. Let me be precise about what these numbers mean, because the spread between them is the entire point. The annual probability of a magnitude 7 or greater earthquake at Yellowstone is roughly 1 in several hundred. The annual probability of a caldera-forming eruption is roughly 1 in 700,000. The ratio between those two probabilities is on the order of 1,000 to 1. The earthquake is roughly 1,000 times more likely per year than the super-eruption. The hydrothermal explosion is, per year, and integrated across all the basins, somewhere in between but closer to the earthquake end, multiple expected events per decade, depending on the size class. Yet if you stop 100 people on a street anywhere in the United States and ask them what the dangerous thing about Yellowstone is, 90-something of them will give an answer in the category of the super-eruption. They will say it is overdue. They will say the magma chamber is filling. They will say the government is hiding it. None of those statements is consistent with the data. The magma chamber is not filling in a way that would suggest imminent eruption. The eruption is not overdue in any technical sense because the recurrence interval has too much variability, and the sample size of past eruptions is too small to construct a meaningful overdue framework. The government is not hiding it, because all of the underlying data is open and is analysed by researchers around the world, including by researchers outside the US who have no incentive to align with any particular government framing. This is the inversion. The public has been trained by decades of documentaries and news stories and dramatized features to fixate on the least likely category of hazard at Yellowstone, while paying essentially no attention to the second most likely category, which is the one most likely to actually harm a tourist on a given day. The thing that the 2026 sequence at Black Diamond Pool is doing, in a quiet and persistent way, is producing a visible record of the hazard category that the public has been ignoring. The April 28th event is, in size class, almost exactly the kind of event that the USGS hazard assessment ranks as most relevant to human harm at Yellowstone on a human lifetime timescale. It is the canonical real-world example of the second item on the list, the one the public mental model has skipped past on its way to the fifth item. If anything is going to kill a Yellowstone tourist in your lifetime, not in some abstract civilization scale sense, but specifically a person walking the boardwalks on a Tuesday morning, it is not the super eruption. It is an event very much like the April 28th one, except occurring at a time when the boardwalk is open, in a basin where tourists are standing, with a debris pattern that intersects with where the tourists are. That is the actual hazard. It is the hazard the data ranks as most relevant, and it is the hazard the April 28th footage is, in a single moment, demonstrating. Part 6. The annual probabilities, honestly. Let's go through the numbers slowly, because the numbers are where the inversion of the public mental model becomes impossible to ignore. The most current USGS hazard assessment lists annual probabilities for each event category. Let me read them to you, and let me put them next to each other in a way that should be clarifying. The annual probability of a caldera forming supereruption at Yellowstone is approximately 1 in 700,000. Expressed as a decimal, that is roughly 0.0000014. In 100 years, the probability of seeing such an event is 1 part in 7,000. In 1,000 years, it is 1 part in 700. The recurrence interval, the average time between such events, is in the range of 600,000 to 800,000 years. The last such event at Yellowstone was approximately 630,000 years ago. You can do the arithmetic to get a sense of where we are in the cycle. But the recurrence is so variable in the geological record, and the sample size of past events is so small, that any precise overdue by X years framing is not statistically meaningful. The honest framing is that the rate is low, and that we are roughly within the typical range of intervals between events, neither obviously due nor obviously safe in a statistical sense. The annual probability of a magnitude 7 or greater earthquake in or near the Yellowstone caldera is on the order of 1 in 300 to 1 in 500, depending on which fault mapping and historical record analysis you use. In 100 years, the probability of seeing such an event is on the order of 20 to 30%. In 1,000 years, it is overwhelmingly likely. The historical record contains the 1959 Hebgen Lake event, which produced a landslide that killed 28 people, and the 1975 Norris earthquake, magnitude 6.1, which did not have the same fatal consequences but produced damage and modified the behavior of several geothermal features. These events were within human memory, within the recorded American historical period, and they are real demonstrations of the magnitude of earthquake the system produces. The annual probability of a hydrothermal explosion of size class comparable to or larger than the 1989 Porkchop event, integrated across all the basins in the park, is on the order of 1 in a few decades. In 100 years, the expected number of such events is somewhere in the range of 3 to 10. In 1,000 years, it is in the range of 30 to 100. The historical period covers about 150 years of relatively continuous observation, and the count of events in that period, taking only those large enough to leave clear evidence, is in the range of 12 to 24. That is consistent with a recurrence interval of roughly 1 event per decade or so, across the entire park. The annual probability of a Black Diamond Pool scale event, small, locally significant debris ejection limited to the immediate basin, is, integrated across all the active features in the park, on the order of 1 to several events per year. The reason you don't hear about most of them is that they happen at features without dense instrumentation, in basins where the boardwalk is far from the active feature, or at times when no one happens to be standing where they could see. The 2024 event was not statistically unusual at the park-wide level. What was statistically unusual about it was the combination of the size, the location, and the presence of tourists with phones who happen to capture it. Take any of those three factors out, and the event would not have entered the public consciousness at all, even though events of similar size occur multiple times a year somewhere in the park. Now let's put these numbers next to each other in a way that should make the inversion stark. Per year at Yellowstone, the expected number of magnitude 7 or greater earthquakes is on the order of 0.003. The expected number of pork-chop-scale hydrothermal explosions is on the order of 0.03. The expected number of black diamond-scale hydrothermal explosions is on the order of 1 to 5. The expected fraction of a caldera-forming supereruption is on the order of 0.00000014. The ratio of expected small hydrothermal explosions to expected caldera-forming eruptions per year is on the order of 10 million to 1. Read that ratio again, 10 million to 1. In a given year, you should expect 10 million times more small hydrothermal explosions than caldera-forming eruptions at Yellowstone. The public's mental model has these in the opposite order of importance. There is a deeper point hiding inside that 10 million to 1 ratio that is worth pausing on, because it is the kind of number that the human mind is not built to handle, and that the public conversation about Yellowstone has not been built to handle either. Probability ratios of 10 million to 1 are essentially incomprehensible at an intuitive level. The brain, when given a number that large, does what it does with all such numbers. It rounds it off into one of two bins. The bin for things that happen, and the bin for things that do not happen. Caldera-forming eruption goes into the bin for things that happen, because someone said the word eruption, and the brain knows that eruptions happen. Hydrothermal explosion goes into a less salient bin, because the phrase is unfamiliar, and the brain has not been trained to weight it. The 10 million to 1 ratio of expected frequencies between them collapses, in the human mind, into a much smaller perceived difference. We feel both as roughly equally likely, and so we fixate on the dramatic story and underweight the actual one. A 2018 study of public perception of Yellowstone hazards, conducted by researchers at several US universities and cited extensively in USGS public outreach materials, found that the dominant mental model among non-specialist members of the public was the caldera-forming super-eruption. The hydrothermal explosion was not part of the public mental model for most respondents. Many respondents had not heard the term hydrothermal explosion. When asked to rank the relative danger of different categories of Yellowstone hazard, the public ranked the super-eruption first, and the hydrothermal explosion last or near last. This is the opposite of the actual USGS ranking. The study also looked at what happens after exposure to information about hydrothermal hazards. The result was unsettling. After being told the actual ranking, with the actual numbers, most respondents updated their stated beliefs about which hazard was most likely. But when surveyed again weeks later, the original mental model had largely reasserted itself. The supereruption is, for most people, an easier story to hold in memory. It has been told to them many times. It has been depicted in films and documentaries. It has a name. The hydrothermal explosion is a phrase that is harder to remember, harder to visualize, and harder to fit into a mental frame that was built around the supereruption story. The 2024 Black Diamond Pool footage was, in a sense, the first time the hydrothermal explosion had a piece of viral media attached to it. After the July 23rd event, search interest in the term spiked dramatically. People who had never heard the phrase typed it into search engines. Articles were written, podcasts discussed it. The term entered the popular vocabulary for the first time, but the structural understanding, the understanding of why hydrothermal explosions are the more likely hazard, and how they differ from magmatic eruptions, and what it means that the supereruption is the least likely category, did not improve substantially in the public conversation. The footage was treated as a curiosity. It was processed in most cases as a tangent to the main Yellowstone story, which remained the supervolcano. The structural lesson, that the actual threat is something other than what the public has been led to believe, did not land. The 2026 sequence is the second opportunity. 5 events at the same pool in 5 months, with the April 28th one on a webcam in clear morning light, is an opportunity to land the structural lesson that the 2024 event did not land. Whether it will land this time depends in significant part on how the story is framed, who tells it, and whether it gets caught in the same algorithmic and editorial framing that processes everything Yellowstone related as a tangent to the supervolcano story. The video you are watching right now is one attempt to frame it correctly. It will not be enough on its own. But the data has been pointing this direction for 40 years, and the empirical record at Black Diamond Pool is providing in real time the kind of demonstrable evidence that the data needs in order to be heard. The numbers are not ambiguous, the ranking is not contested by serious researchers, the footage exists, the pool is still exploding, the opportunity to tell the right story is in front of us. What we do with it is a question that the public perception research suggests we are likely to handle poorly. But the fact that we are likely to handle it poorly is not the same as the fact that it should be handled poorly. The data says what it says. The actual Yellowstone threat is what it is. And the pool, in the meantime, will probably explode again before the year is out, on a date and at a time that the sensor network will record, that the webcam will or will not capture depending on the weather, and that will once again give us an opportunity, however brief, to look at what is actually dangerous about this place. Part 7. Biscuit Basin's Geology and History. To make sense of why Black Diamond Pool, of all the thousands of features in Yellowstone, is the one producing 5 events in 5 months in 2026, you need to know a little about the basin it sits in. Biscuit Basin is a small thermal area on the west side of the Upper Geyser Basin region of Yellowstone, just a few hundred meters west of the Old Faithful complex. It sits inside the Yellowstone caldera, in the caldera's southwestern quadrant, on a substrate of glacial and lake sediment overlying rhyolitic volcanic rocks that were in place during the post-caldera resurgent eruptions of the past several 100,000 years. The basin's name comes from biscuit-shaped sinter deposits that historically surrounded the basin's larger features, and that were, in the early 20th century, broken or modified by visitors before the park's protection regime got serious. Many of those original sinter biscuits no longer exist, but the name persists. The basin contains a variety of geothermal features. The largest and best known is Sapphire Pool, a hot spring with strikingly blue water on the eastern side of the basin. Sapphire Pool went through a dramatic transition in 1959, immediately after the Hebgen Lake earthquake. The earthquake, which had its epicenter outside the caldera, but which produced significant seismic energy that propagated across the entire region, triggered changes in many of Yellowstone's geyser features. Sapphire Pool, before the earthquake, was a relatively quiet hot spring. After the earthquake, the pool became dramatically more energetic. Eruptions of water tens of meters into the air began to occur. The pool's surface boiling intensified. The connection, earthquake-triggering changes in hydrothermal feature behavior at distances of tens to hundreds of kilometers, is well documented in the Yellowstone scientific literature, and the Sapphire Pool transition is one of the canonical examples cited in introductory volcanology textbooks. Other named features in Biscuit Basin include Jewel Geyser, which erupts every 5 to 10 minutes to a height of about 6 meters. Black Pearl Geyser, which has had periods of activity and quiescence over the past century, and a number of smaller pools and fumaroles. Black Diamond Pool, before the 2024 event, was not on most visitor itineraries. It sat on a secondary spur of boardwalk, away from the basin's main loop, and most visitors walked past it without paying particular attention. Its surface was, in 2023 and earlier, a more or less continuously calm pool of blue-green water with low-volume gas emissions producing slight ripples. It was, by every appearance, a quieter and less impressive cousin of Sapphire Pool located across the basin. The water that emerges in Biscuit Basin's features is meteoric in origin. That means it falls as rain or snow on the surrounding Yellowstone Plateau, percolates through the rhyolite over years to decades, descends to depths of perhaps several hundred meters to 2 kilometers, where it is heated by the magma chamber and by residual hot rock from past intrusions, and then rises again through fault and fracture pathways to emerge in the basins at the surface. The chemistry of the water that emerges in Biscuit Basin, as in most of the Upper Geyser Basin, is dominantly alkaline chloride. The pH is on the slightly alkaline side. The water carries significant dissolved silica, chloride, sulfate, and various trace elements. This is distinct from the chemistry of the features at Norris Geyser Basin, where the water is more acidic, or at Mud Volcano, where the water carries high concentrations of sulfate and produces acid-altered surroundings. The chemistry of the water tells you something about its history, about the rocks it has flowed through, about the temperatures it has reached, about the depths it has visited. The reservoir that feeds Biscuit Basin's features sits at depths of, very roughly, several hundred meters to a couple of kilometers. The magma chamber itself, which provides the deep heat, sits at depths of 5 to 10 kilometers beneath the caldera floor. The intermediate region between the reservoir and the magma is filled with hot rock that has been heated by past intrusions over hundreds of thousands of years and that continues to be heated by the magma chamber's continued presence. The water in the deep reservoir is at temperatures on the order of 250 to 350 degrees Celsius. The pressure at those depths is sufficient to keep the water liquid even at those temperatures. As the water rises through the conduits toward the surface, the pressure decreases and the water transitions through the two-phase region into mixed water and steam, and then into mostly steam at the surface. Biscuit Basin has a documented record of hydrothermal explosions extending well back into the prehistoric record. The basin's surface and immediate surroundings show evidence of past explosion craters and ejected debris fields. Sapphire Pool itself, beyond the 1959 Hebgen Lake transition, has produced documented small explosive events. Black Diamond Pool, before the 2024 event, had produced small explosions at irregular intervals over the past several decades. The basin is, in volcanological terms, a known active hydrothermal explosion site. What changed in 2024 is the magnitude and the visibility of the activity at one specific pool. The location of Black Diamond Pool within the basin is geologically significant. The pool sits along a structural lineament, essentially a small fault, that crosses the basin from northwest to southeast. Several of the basin's most active features lie along this lineament. Fault zones in hydrothermal systems are preferred pathways for fluid flow because the fractured rock along the fault has higher permeability than the surrounding intact rock. Higher permeability means easier flow of hot water from depth, which means more active features at the surface. The fact that Black Diamond Pool is on this lineament is part of why it is one of the more active features in the basin in any given year, and part of why it is more responsive to perturbations than features located off the lineament. The 2024 event modified Black Diamond Pool's local geology in ways that the post-event surveys have documented in detail. The pool's vent, the opening at the bottom of the pool through which water enters, was widened. The conduit beneath the pool was partially cleared of accumulated mineral material. The sinter apron surrounding the pool was disturbed by the ejection event. New cracks in the apron, some of them now visible from the relocated boardwalk, formed in the immediate aftermath of the event. None of these modifications were severe enough to fundamentally alter the pool's character, but all of them shifted the pool's local geometry away from its long-term equilibrium and toward a state that, in the post-2024 period, has been producing the small events of the 2026 sequence. The other features in Biscuit Basin, as of May 2026, have not shown obvious changes that would indicate basin-wide reorganization. Sapphire Pool is roughly behaving as it did in the post-Hebgen Lake era. Jewel Geyser is erupting on roughly its usual interval. Black Pearl Geyser is in one of its quieter phases. The basin as a whole, observed at the level of resolution that the sensor network and the visual record can provide, looks more or less unchanged from the year before the 2024 event, with the exception of Black Diamond Pool. This is consistent with the conduit modification interpretation of the 2026 sequence. It would be less consistent with a basin reorganization interpretation, which would predict changes at multiple features. Of all the features in Biscuit Basin, Black Diamond Pool is by a substantial margin the most densely instrumented today. The seismometer, the infrasound array, the water level pressure transducer, the temperature thermistor, the dissolved gas sampler, and the webcam together constitute a level of monitoring that exceeds what almost any other named feature in the entire park has ever received, which means that what we know about the 2026 sequence at Black Diamond Pool, we know with a precision that is unusual in the history of Yellowstone monitoring. The sequence has been observed in a level of detail that simply was not available for the earlier explosive sequences at other features in the park's history. If the same sequence had occurred at Sapphire Pool, or at Black Pearl, or at any of the dozens of less instrumented features, the public would have far less information about it. We would know that explosions had occurred. We would not know, to the second, when each one happened, what the seismic and infrasound signatures looked like, what the water level changes were in the precursor window, what the dissolved gas concentrations did. We would have rough counts, post-event surface observations, and a vague sense that something was happening. The Black Diamond Pool sequence, by virtue of where it is and what was installed there after 2024, is producing a level of empirical detail that the broader study of Yellowstone hydrothermal explosions has not previously had access to, which brings us naturally to the question of size. The 2026 events at Black Diamond Pool are small. The 2024 event was larger but still locally limited. To put these in context, we need to look at the upper bound of what this system has demonstrably produced. The events that, while geologically rare, define the size class that the same physical mechanism can support if the conditions are right. That brings us to two reference events. One occurred about 13,000 years ago at the northern end of Yellowstone Lake. The other occurred in 1989 at Norris Geyser Basin in front of a much smaller number of witnesses than the 2024 event. Both are useful as comparison points. Both, importantly, sit on the same continuum of physical processes that produced the April 28th event. The difference is only in scale. Part 8, Mary Bay and the 1989 Porkchop event. The largest hydrothermal explosion in the geological history of Yellowstone for which we have a clear physical record is the Mary Bay event. The Mary Bay event happened approximately 13,000 years ago at the northern end of Yellowstone Lake, where the bay that now bears its name forms an arc-shaped indentation into the lake's shoreline. The event left a crater. The crater is approximately 2.5 kilometers across. It is, by every measure, the upper bound of the empirical distribution of Yellowstone hydrothermal explosions in the late Pleistocene and Holocene record. To make the size of this event tangible, a 2.5-kilometer crater means that if you stood at the center of it, you would have to walk for the better part of half an hour in any direction to reach the rim. The crater is large enough that the bay itself, the geomorphic feature that defines that part of the lake's shoreline today, is the crater. The bay was created by the explosion. The water-filled depression at the lake's edge is what remains of the void produced 13,000 years ago, when a portion of the Yellowstone Lake's lake bed, along with everything immediately above and around it, was ejected upward and outward in what must have been one of the most violent events that has occurred at Yellowstone in the post-glacial period. The ejecta from the Mary Bay event have been found in geological surveys at distances of several kilometers from the source. Blocks of rock the size of small houses have been mapped on the surrounding plateau. The energy of the event, estimated from the crater volume and the ejecta distribution, is on the order of tens of megatons of TNT equivalent. That is, on the scale of weapons, in the range of large nuclear devices. The event would have, if observed by humans living near the lake at the time, been catastrophic at distances of many kilometers. If a similar event were to occur today at the same location, the destruction would extend across most of the northeastern quadrant of the park, including the lake village area and the road network around it. The mechanism of the Mary Bay event was in essence the same mechanism we have been discussing. A region of superheated water beneath a sealed conduit failed catastrophically. The water flashed to steam. The expansion drove the ejection. The difference was the scale. The volume of water involved was on the order of cubic kilometers rather than cubic meters. The depth of the sealed region was on the order of hundreds of meters. The trigger may have involved an earthquake or some other large perturbation that breached the seal across an unusually large area, all at once, rather than the slow, gradual failure that characterizes smaller events. The same physics produced a vastly larger outcome. The recurrence interval for Mary Bay scale events in the Yellowstone record is poorly constrained because the sample size is so small. Mary Bay is the largest documented event. The Indian Pond event, perhaps 3,000 years ago, was somewhat smaller but still produced a crater hundreds of meters across. The Turbid Lake event, perhaps 9,400 years ago, was also in the intermediate range. The Pocket Basin events, which involve a cluster of smaller craters on the western side of Yellowstone Lake, date variously to the late Holocene. The complete list of events in this size range, based on surface mapping and dating, is small enough that the recurrence interval estimate has substantial uncertainty. The current best estimate is on the order of one event of Mary Bay scale or larger per several thousand years. That is a low rate. Over a human lifetime, the probability of seeing such an event is in the range of 1 or 2%. Over a century, it is a few percent. Over a millennium, it becomes more likely than not. Over the next 10,000 years, it is nearly certain. The Mary Bay event is the upper bound. It is the thing that, at the extreme end of the distribution of what the Yellowstone hydrothermal system can produce, has actually happened. It tells us what the system is capable of. It does not tell us when. The recurrence interval is too uncertain, and the dating of past events is too imprecise for any meaningful prediction of when the next such event will occur. But it tells us that the question of what the upper bound is not academic. The system has produced events of that scale before. The system is, in geological terms, the same system it was 13,000 years ago. The lake is in the same place. The caldera is in the same place. The magma chamber is in the same place. And the slow processes that produced the sealed reservoir that failed to produce the Mary Bay crater are the same processes that are operating today, somewhere in the system, building toward the next event in that size class. Now consider the other end of the historical record, the 1989 Porkchop Geyser event at Norris Geyser Basin. Norris is in a different part of the park from Biscuit Basin. It is a separate thermal area with different water chemistry with a different set of features. Porkchop Geyser is, or rather was, a small feature on the south side of Norris's back basin. Before 1989, Porkchop had behaved as a regular small geyser, producing eruptions of water on a roughly predictable schedule. On September 5th, 1989, with no warning, the feature underwent a hydrothermal explosion. The event was small by the standards of Mary Bay, but it ejected rocks tens of meters from the feature. It ejected mud and water dozens of meters into the air. It completely modified the surface geometry of the feature. Where Porkchop had been a small geyser, after the event there was a small crater. The geyser, in its previous form, no longer existed. There were people in the basin at the time. There were not, in 1989, the boardwalk densities that exist at Norris today, but tourists were present. None of them were directly struck by ejecta. The closest people were on the order of 50 meters away when the explosion occurred. Rocks landed within a few meters of them. No one was killed. No one was injured. The pure geometry of the ejection pattern saved the lives of the people who happened to be standing where they were standing. The Porkchop event was, for the modern era of Yellowstone observation, the reference event for what a moderate hydrothermal explosion looks like. Before the 2024 Black Diamond Pool event, when researchers and journalists wanted to talk about what a hydrothermal explosion at Yellowstone was, they reached for Porkchop. The video record of Porkchop is sparse. There are a few photographs from immediately after the event. There are no clear videos. The footage record we now have of the 2024 Black Diamond Pool event and the partial record we have of the April 28, 2026 event is dramatically more complete than anything that existed for Porkchop. In a sense, the 2024 event displaced Porkchop as the reference event in the public mind. But for researchers, Porkchop remains the more carefully analysed of the two because the time since the event has allowed for decades of follow-up study. What Porkchop demonstrates is that a moderate hydrothermal explosion can happen in a basin open to the public, on no warning, with no precursor sequence that anyone identified. The same mechanism that produces the small events at Black Diamond Pool produced Porkchop. The same mechanism that produced Porkchop, scaled up by some factor that depends on the volume of trapped water and the depth of the seal, produces events of the Mary Bay scale. There is, in the underlying physics, a continuous spectrum from the smallest detectable explosion to the largest possible event the system can support. The continuum is real. The probability distribution along that continuum is real. And the small events at Black Diamond Pool are, in this sense, not just a curiosity from one closed-off basin. They are samples from the distribution. They are the system telling us in real time what it is doing at the low end. The same distribution that produces those events produces, less frequently, the events that scale up. The thing that bracketed Black Diamond Pool then is this. At the small end of the distribution, the 2026 sequence, events that mostly happen at night, mostly need instruments to be detected, sometimes throw a few rocks. At the medium end, Porkchop, 50 meters of ejection, a feature destroyed, tourists nearby spared only by geometry. At the large end, Mary Bay, 2.5 kilometer crater, kilometers of ejecta, a region of the park reshaped. The April 28th event sits firmly at the small end. The same physics, operating on a different scale, sits at the other two endpoints. The fact that we have all three of these in the record, that they are mechanistically continuous, that they are samples from the same distribution, is what makes the 2026 sequence at Black Diamond Pool a window into the system as a whole, rather than just a local curiosity. It is the system showing us, on the small end, that it is the same system that produced Porkchop, and that produced Mary Bay. The size in any given event is a matter of accident. The fact that events happen is a matter of structure. Part 9. The public mental model versus the data. There is a peculiar kind of cognitive trap that has organized itself around the public understanding of Yellowstone, and it is worth slowing down here and looking at it directly, because the trap is the reason why a sequence like the one at Black Diamond Pool gets processed by most people as a footnote, rather than as the main story. The trap is the supervolcano mental model. The mental model is, roughly, this. Yellowstone is a giant volcano. It has erupted catastrophically in the deep past. It will erupt catastrophically again. It is overdue, or it is filling, or it is rumbling. The signs of its impending eruption are visible if you know what to look for. The government either knows what is coming and is hiding it, or is itself in the dark. When the eruption comes, it will be civilization-altering. Clouds of ash blanketing North America, climate cooled for years, food systems collapsed, millions displaced or worse. This is the model. It is so dominant in the popular discourse that it functions for most non-specialist Americans as the only way of thinking about Yellowstone at all. Each piece of this model is, on its own terms, defensible. Yellowstone is a giant caldera. It has erupted catastrophically in the deep past 3 times in the last 2 million years. It will probably erupt catastrophically again at some point in the geological future. The signs of impending eruption would, in principle, include certain kinds of ground deformation, certain kinds of seismic patterns, and certain kinds of gas emissions. The consequences of such an eruption would, in fact, be on the scale that the popular narratives suggest. None of those individual pieces is wrong. What is wrong is how the pieces have been assembled into a story about the present. The probability that the catastrophic eruption will occur within the next century, or within a human lifetime, is the part of the model that the public has gotten wrong, and it is the part that matters. The recurrence interval is on the order of 600,000 to 800,000 years. The last such eruption was approximately 630,000 years ago. We are within the typical range of intervals between events. We are not provably overdue, and we are not provably safe. The variability in past intervals is too large to make either statement with confidence. The annual probability of a caldera-forming eruption is, on the best current estimates, on the order of 1 in 700,000. That is small. That is, in fact, the smallest annual probability of any of the hazard categories on USGS's list. It is the least likely event the system can produce per year of all the dangerous things the system can do. The signs of impending eruption that the public looks for are, in many cases, real geological phenomena that occur at Yellowstone but that do not indicate what the public model says they indicate. The caldera floor deforms. It rises in some years, subsides in others. The cumulative deformation over the past century is on the order of tens of centimeters. This is normal background behavior of a large caldera system with an underlying magma chamber that exchanges fluid and gas with the surrounding rock. It is not, by itself, a sign of imminent eruption. Geysers change their behavior. Steamboat Geyser, for example, has had decades of quiet punctuated by years of frequent eruptions, and the transition between those states is not a sign of magmatic input. Earthquakes happen in swarms. Yellowstone has between 1,500 and 2,500 earthquakes per year, almost all of them small, organized into swarms that come and go. Swarms are not, by themselves, signs of impending eruption. They are background behavior of a system with a high heat flow and a complex shallow seismicity environment. The public model interprets each of these phenomena as a precursor sign. The model says the caldera is rising, the geysers are changing, the earthquakes are swarming, therefore the eruption is coming. But each of these phenomena is, against the background of the system's actual behavior, well within the range of what the system does on any given decade or century, regardless of whether an eruption is coming. The pattern recognition that the public mental model performs is, in technical terms, false positive recognition. It identifies signal where there is only baseline. What the public mental model misses is what the actual hazard data shows. The actual hazard in any given year is hydrothermal, small events that occasionally scale up to events of consequence, in basins where tourists walk on boardwalks separated from the active features by tens of meters or less. The actual hazard is seismic, earthquakes that can damage infrastructure and that have, in the historical record, killed people in the region surrounding the caldera. The actual hazard is, in the medium term, what the system is most likely to produce and what we should be paying the most attention to. The caldera-forming eruption is the dramatic worst case. It is the worst case in the same sense that a major asteroid impact is the worst case for the planet. Real, possible in some geologically long time frame, almost certain not to occur in your lifetime. There is an additional layer here worth noting. The same pattern recognition that produces the public mental model also drives the mainstream media coverage of Yellowstone. When a science journalist writes a Yellowstone story, the editorial pressure is to tie it to the super-eruption frame, because that is the frame readers respond to. A story about the actual hazard ranking with the actual numbers attracts fewer clicks than a story about the super-eruption. The economic incentives of the media ecosystem therefore reinforce the misperception, even when individual journalists understand the data correctly. The result is a self-reinforcing loop. The public believes the super-eruption is the dominant hazard. The media writes about it as if it were. The public's belief is confirmed by the coverage. The actual hazard, which is less narratively dramatic, gets covered occasionally, but never displaces the dominant frame. The loop has been running for decades. It will require something more than a single video, even a long one, to break it. A useful analogy. If you live in California, the dangerous thing about California earthquakes is not the megaquake on the San Andreas. Even though the megaquake is the most cinematic version of the hazard, the dangerous thing is the moderate quake, magnitude 5 to 6.5, that is statistically much more likely to occur in your lifetime, that will damage older buildings and unanchored infrastructure, that will start fires and break pipes and kill people in concentrated areas. The megaquake is real, and it deserves attention from infrastructure planners, but the actual day-to-day hazard is the moderate quake. People who live in California understand this in their bones. People who think about California from outside often do not. The Yellowstone analogy is similar. The dangerous thing about Yellowstone is not the super-eruption. The super-eruption is real, and it deserves attention from people who plan on timescales of tens of thousands of years. The actual day-to-day hazard, the hazard that will hurt a tourist this decade, is the hydrothermal explosion. The fact that the super-eruption is more cinematic and more often depicted and more easily talked about does not change which hazard is more likely to actually affect a human life. The 2024 Black Diamond Pool event, by producing the first piece of viral footage of a hydrothermal explosion, had the opportunity to begin shifting the public mental model. It did not, in any structural sense, succeed. The footage was processed as a curiosity. The general public consumed it, briefly searched the term and went back to thinking about the supervolcano. The 2026 sequence is the second opportunity. 5 events in 5 months, with one of them on a webcam in clear morning light, is more raw material for shifting the model than the 2024 event provided. Whether it will succeed where the earlier event did not, depends in part on how the sequence is framed in the public conversation. The framing in this video is one attempt. It will not be enough on its own. But the data has been pointing this direction for 40 years, and the empirical record at Black Diamond Pool is providing in real time the kind of demonstrable evidence that the data needs in order to be heard. Part 10. The Conspiracy Framings, Engaged Honestly. There is a category of public discussion around Yellowstone that needs to be engaged directly rather than dismissed, because the dismissive approach has not worked, and because the honest engagement is, in any case, more interesting than the dismissive one. The category is the conspiracy framing, the family of claims that hold, in varying strengths, that the federal scientific establishment is concealing information about what is happening at Yellowstone, and that the public would, if it knew the truth, react very differently than it does. The strongest version of this claim is that USGS is actively suppressing or downplaying information about Yellowstone's near-term hazard, because the economic and political consequences of public disclosure would be unacceptable. Under this framing, the 2026 sequence at Black Diamond Pool is the visible tip of a much larger pattern of activity that USGS is choosing not to fully describe, and the small events being publicly reported are a euphemism for a developing crisis at depth that USGS knows about and is suppressing. The empirical case against this framing is straightforward and worth laying out, because it disposes of the conspiracy claim in a way that does not require the audience to trust USGS. The case rests on 3 points. First, the underlying data from Yellowstone monitoring is publicly available. The raw seismic waveforms from the YVO network are published in near real time on the USGS Earthquake Hazards Program Data Server. The GPS deformation data is available on UNAVCO. The INSAR data from satellite passes is available through public agency channels. The webcam feeds are public. The water level and temperature data from the instrumented features, including Black Diamond Pool, is published on YVO's public dashboard. This means that anyone with the relevant technical skill can analyze the data themselves, independently of USGS's interpretive framings. They do not have to trust USGS to tell them what is happening. Second, researchers around the world, including researchers based outside the United States, with no institutional reason to align with the US government's framings, analyze this data and publish papers based on their analyses. The published literature on Yellowstone monitoring includes work by researchers in Italy, in Germany, in Japan, in the United Kingdom, in Canada, and in other countries. These researchers have, in numerous documented cases over the years, disagreed with USGS's interpretations on specific points. There are published papers that argue that certain monitoring signatures should be interpreted as more concerning than USGS has characterized them. There are published papers that argue that certain deformation patterns may indicate processes USGS has not adequately addressed. These papers exist, they are part of the open scientific discourse, and they have been responded to by the broader community in the normal way. None of them have shown, however, evidence of suppression. None of them have shown a coordinated pattern across the data that would indicate USGS was concealing a developing crisis. If the data showed such a pattern, the independent researchers would have found it, because they have the same data and they have demonstrated their willingness to disagree. Third, the historical pattern of USGS's public communications around Yellowstone events has been one of acknowledging uncertainty rather than concealing it. After the 2024 event, USGS issued multiple bulletins describing the event, the mechanism, the modifications to the pool, the implications for monitoring, and the uncertainties in the interpretation. After significant seismic swarms, USGS has communicated about them in real time, often in ways that have, if anything, increased rather than decreased public alarm. The agency's track record is not one of suppression. It is, if anything, one of more communication than the public has been prepared to absorb. This disposes of the strong version of the conspiracy claim. The data is open, the analysis is independent, and the communications are extensive. There is a weaker version that is harder to fully falsify, because it is structurally a claim about private belief. The weaker version holds that USGS researchers privately believe more than they say in public, and that institutional caution leads them to understate what they know. This is, in principle, an unfalsifiable claim, because no amount of public communication can demonstrate that private belief is consistent with public communication. However, the way to engage this honestly is to note that the published scientific literature includes a range of viewpoints, and that the range includes views that are more pessimistic than USGS's official public framings. Researchers who privately held more pessimistic views would, presumably, publish papers expressing them, and other researchers do exactly that on a range of topics related to Yellowstone. The published spread of views is consistent with the public-private framings being roughly aligned. There is no large gap between what working scientists say in public and what they say in published papers. Now, there is a legitimate question that sits adjacent to the conspiracy framings, and that deserves its own treatment because it is not a conspiracy claim. It is a policy and ethics question. The question is whether the National Park Service's continued public access to other parts of the Upper Geyser Basin is appropriate given the demonstrated hazard at Black Diamond Pool. The 2024 event happened on a boardwalk that was open to the public. Tourists were within tens of meters of an explosion that ejected rocks the size of small cobbles. No one was killed only because of pure geometry. The relocated boardwalk at Biscuit Basin has been closed to the public since, but Old Faithful, the Old Faithful Inn, the visitor centres, the broader Upper Geyser Basin trails, all of these remain open. All of these sit within a thermal area that has, in its historical and prehistoric record, produced hydrothermal explosions. The decision to keep them open is a deliberate one, rooted in an assessment that the per-day risk is acceptable. That assessment is grounded in data. The per-day probability of an event of harmful size at a tourist-occupied location is genuinely small. But the assessment is an assessment, and the question of whether it has been adequately communicated to the public and whether the public has had the opportunity to make an informed choice about whether to accept the residual risk is a legitimate one. It is not a conspiracy question. It is a question about transparency and informed consent. There is also a budgetary question that sometimes gets conflated with the conspiracy framings. The monitoring at Black Diamond Pool was funded in part by emergency supplemental allocations after the 2024 event. The monitoring at most other features in the park is less dense than it is at Black Diamond Pool. Some features that have, in the geological record, produced moderate or larger hydrothermal explosions have very little instrumentation today. The case for expanded monitoring of more features is publicly made by USGS itself in its budget requests, and the funding decisions are made by Congress through the appropriations process. This is not concealment, it is a resource constraint. The agency would, in its own statements, prefer more monitoring than it has. Whether Congress provides that is a political question, not a scientific one. There is, finally, a more diffuse public discourse phenomenon that is worth naming. Yellowstone serves as a kind of catch-all symbol in the American imagination for the catastrophe that is coming. It absorbs a range of anxieties about climate, about systemic collapse, about distrust of institutions, and projects them onto the geological story. The super-eruption framing, with its civilization-altering imagery, fits the role of catastrophe symbol better than the hydrothermal explosion framing does, because the hydrothermal explosion framing is geographically limited and does not function as a symbol for the end of an era. When the public talks about Yellowstone as if it is overdue, or as if the government is hiding the truth, what is sometimes being expressed is something other than a literal claim about geology. It is sometimes a way of expressing distrust of institutions in general, or anxiety about long-running systemic risks, or a sense that something important is being kept from us. Engaging with the conspiracy framings honestly requires acknowledging that some of the energy behind them is about something other than Yellowstone, and that the honest response is to engage with the underlying anxieties even while disagreeing with the geological claim. None of this changes what the underlying data says. The super-eruption is the least likely category of event at Yellowstone per year. The hydrothermal explosion is the second most likely category. The 2026 sequence at Black Diamond Pool is the second most likely category, showing up in our instruments and on our webcams, in real time, in a way that the public can engage with if it chooses to. Whether the public engages with it as itself, or processes it as another verse of the super-eruption song is the question. And the conspiracy framings, however honestly engaged, are part of why the engagement has been so difficult so far. Part 11. The Global Hydrothermal Context. A version of this conversation is happening right now around a handful of other hydrothermal and shallow volcanic systems on Earth, and the parallels are worth surveying briefly because they help disentangle which patterns in the 2026 Black Diamond Pool sequence reflect something specific to Yellowstone, and which patterns reflect more general behaviour of the kind of system Yellowstone is. Iceland's Reykjanes Peninsula has been in an active phase since 2021. The Fagradalsfjall and Sunnukur eruption sequences have produced multiple effusive eruptions along the peninsula's volcanic systems. The activity has affected a town, has rerouted a road, and has produced a level of small-volume volcanism in a densely inhabited area that Iceland had not seen in centuries. Reykjanes is a different kind of system than Yellowstone. It is a mid-ocean ridge system above sea level, with frequent basaltic magmatism, rather than a continental rhyolitic caldera, but it shares with Yellowstone a high heat flow, geologically young, volcanically active character. What is happening at Reykjanes is what Reykjanes does on multi-century timescales. The current activity is at the high end of recent history, but not unprecedented in the longer record. The public discussion in Iceland has been more grounded than the public discussion of Yellowstone, in part because the system is more visible in everyday life, and in part because the warning systems work and the residents see the data. New Zealand's Taupo volcanic zone has had elevated thermal activity at several features over recent years. The zone runs north-northeast from the central North Island and includes Lake Taupo itself, a caldera comparable in scale to Yellowstone that has produced very large eruptions in its geological history. Several geyser fields in the zone have shown unusual behaviour, and the volcanic alert level at several specific volcanoes has fluctuated. The Taupo discussion in New Zealand has been measured, and the New Zealand monitoring agency GNS Science has had public communications that are reasonably effective at distinguishing routine variation from concerning signals. The system is not, however, in a state that suggests imminent caldera-forming eruption, despite the elevated activity at individual features. Italy's Campi Flegrei caldera, west of Naples, is in a phase of sustained ground uplift that has now persisted for more than a decade. The uplift, combined with seismicity that has increased in both rate and magnitude during the same period, has produced active scientific debate about whether the system is approaching an eruption or whether it is in an extended period of unrest that will resolve without a magmatic event. The Italian Civil Protection Authority has, in recent years, raised the alert level for Campi Flegrei and has begun preparation for potential evacuations of populated areas inside and around the caldera. The Campi Flegrei case is, in some ways, the most concerning of the global parallels because the population at risk is large and the uplift is sustained and unambiguous. It is also a case that has been transparently communicated by the Italian authorities, with the alert level changes accompanied by detailed public explanations of what is being seen and what it might mean. There are smaller parallels at other systems. The Long Valley caldera in California has been monitored for decades and has had episodic unrest. The Phlegrean fields of Italy have a longer history of unrest than the current Campi Flegrei episode. The Tatun volcanic group near Taipei has periodic seismic and thermal activity. Each of these is a system that, like Yellowstone, has produced large eruptions in its deep geological past, and each is monitored today at varying levels of intensity. What the global survey shows, taken together, is that hydrothermal and shallow volcanic systems are, by their nature, unsettled. They produce small events on regular intervals. They have periods of elevated activity that can last years to decades, and then subside without producing larger events. The probability that any given period of elevated activity at any given system will escalate to a larger event is, on the empirical record, modest. The probability that some such period will, over a long enough time window, eventually escalate to a larger event somewhere is much higher. The base rates are what they are. The system-specific signals are what they are. The honest scientific framing is that we monitor closely, we treat unusual signals seriously, and we accept that the bulk of unrest episodes resolve without major events. The apparent global pattern, multiple systems showing some kind of elevated activity simultaneously, is most likely a function of two things. First, hydrothermal and shallow volcanic systems are always somewhat active, and at any given time some subset of them are in elevated phases. The fact that the 2026 survey finds several is not, by itself, evidence of a global synchronizing trigger. Second, increased monitoring globally over the past few decades has made unusual activity more visible than it was historically. A system in elevated phase today gets detected and reported. The same system 50 years ago might have shown the same activity without anyone noticing or publicly reporting it. Some fraction of the apparent global pattern is therefore a detection effect rather than a true synchronization. The truth, then, about the Black Diamond Pool sequence in the global context is this. Hydrothermal systems are always somewhat unsettled. What is specific about Black Diamond Pool is not the underlying activity rate, but the density of instrumentation that allows that rate to be measured precisely. The same kinds of unrest are happening at varying intensities at thermal areas all over the world. Yellowstone's sequence at one pool is one expression of a global category of behavior. It is not part of a synchronized planetary event. It is the local manifestation of physics that operates the same way everywhere on Earth, that the right combination of heat, water, and shallow plumbing exists. Part 12. What the next 12 months will look like. So let us land this video. Let us look at what the next 12 months are likely to show, and let us look at the question the public should actually be asking. The honest forward-looking statement based on the data, the published interpretations, and the assessment that YVO is publicly working from is the following. The most probable trajectory at Black Diamond Pool over the next 12 months is continued small events. The conduit modification interpretation predicts that the elevated rate will persist for some period and then decay as the pool's plumbing re-equilibrates. The duration of that decay could be months or years. The published literature on similar post-event sequences at Yellowstone and elsewhere suggests timescales in that range. We should expect, somewhere in the next 12 months, several more small events at Black Diamond Pool, each of them detectable in the sensor network, some of them visible on the webcam, all of them adding to the empirical record. We should not expect any of these events to be dramatically larger than the events of the 2026 sequence so far. The most probable trajectory does not include a pork-chop scale or larger event at Black Diamond Pool in the next 12 months. The probability of such an event at that specific pool is low, though it is not zero. The most probable trajectory for Biscuit Basin as a whole, over the next 12 months, is continued closure of the relocated boardwalk to the public. The basin reorganisation scenario, if it is correct, would imply detectable changes at other features over the same timescale. The sensor network is watching for that. If changes at other features begin to appear, the boardwalk closure could be extended or expanded. If no changes appear, and if the activity at Black Diamond Pool stabilises or decays, a reopening could be considered at some point in the future. The decision will be made by the Park Service in consultation with USGS, on the basis of the monitoring data and on the basis of an assessment of the residual risk to visitors. For the wider park, the next 12 months should look much like any other year. The annual probability of a pork chop scale or larger hydrothermal explosion somewhere in the park is, as we have discussed, on the order of 1 in a few decades. So in any given year, the probability of such an event is roughly 1 in 20 or 30. Multiply that by the probability that any such event occurs in a basin currently open to tourists, with the boardwalk geometry such that ejecta intersect with where the visitors are standing, and you get the actual probability of a tourist being harmed by a hydrothermal explosion in a given year. That probability is small, but it is not negligible. Over a long enough time period, it accumulates to a near certainty. The question is whether, when the event happens, the basin in question has had its monitoring upgraded as Black Diamond Pools has, and whether the data from that monitoring is being processed in a way that could provide even seconds of warning. That is the actual question, not whether the supervolcano will erupt. The supervolcano will, on geological timescales, eventually erupt. It will probably not erupt in your lifetime. It will probably not erupt in your great-grandchildren's lifetime. The annual probability is small enough that, in the time you're likely to keep paying attention, you are vastly more likely to die in a car accident, or from a heart attack, or from any of the dozens of mundane causes that human mortality is actually constituted of. The supervolcano is not the question. The question is whether, the next time you visit Yellowstone on whatever boardwalk you happen to walk past whatever active thermal feature, the system happens that day to produce a moderate hydrothermal explosion. The probability of that on any given visit is small. The probability of it integrated across all visitors and all visits over decades is much larger. Some number of times over the coming decades, an event of that size will occur somewhere in the park while tourists are present. The geometry of how the ejecta intersect with the tourists will be a matter of chance. Some of those events will produce no injuries, some of them will. Probability, played out over time, is going to roll the dice in ways that produce, eventually, the bad outcome. The April 28th event at Black Diamond Pool, the July 23rd event in 2024, the pork chop event in 1989. These are the small and medium samples from the distribution that will, at some point and at some location, produce a sample at the larger end with tourists present. That is the threat. It is real. It is well characterized. It is the second most likely hazard category at Yellowstone after large earthquakes. It is the thing the data has been pointing at for decades. It is the thing the 2026 sequence is, in a quiet and persistent way, making visible. There is a parallel framing that may help drive this home. Consider how the public thinks about lightning. Lightning kills, on average, around 20 people a year in the United States. The probability of being struck by lightning on any given day, in any given location, is extremely small. And yet, when there is a thunderstorm, people who have grown up in lightning-prone regions know to come inside. They do not stand under tall trees. They do not stand in open fields. They have, through cultural transmission and through direct experience, developed an accurate intuition about the modest probability hazard that lightning actually is. They do not fixate on the dramatic outliers, the lightning storm that destroys a city, the rare cluster strike that kills multiple people at once, because those outliers are not the typical hazard. The typical hazard is a single bolt, on a typical day, hitting someone who happened to be standing in the wrong place. The cultural intuition about lightning is correctly calibrated to the typical hazard. The cultural intuition about Yellowstone is not. It is calibrated to the dramatic outlier, the caldera-forming eruption, rather than to the typical hazard, which is the hydrothermal explosion. If a similar cultural calibration around Yellowstone hazards existed, visitors to the park would understand that the boardwalks are not absolutely safe, that the basins have produced events of consequence in the past and will produce them again, that the modest residual risk is real, and that they have implicitly accepted it by visiting. They would treat the boardwalks the way Floridians treat thunderstorms, with respect for the hazard, awareness of its character, and no particular fear because the per-day probability is small. They would not, in this hypothetical, fixate on the super-eruption any more than Floridians fixate on the once-in-a-century hurricane while standing on a beach in May. The cultural calibration would do the work that the super-eruption framing currently displaces. We are not in that hypothetical. The cultural calibration is wrong. The 2024 event and the 2026 sequence are the strongest material the data has produced in decades for correcting the calibration. Whether the correction takes hold is what the next several years of public conversation will determine. If you wanted to spend your worry budget on Yellowstone in a way that was responsive to the data, you would spend it here, not on the super-eruption, not on the ash cloud that will or will not cover North America, on the boardwalk you might walk past, on the basin you might step into, on the pool you might pause to look at, on a day when the conduit beneath it happens to fail. You would notice that the boardwalks at Old Faithful are designed assuming a certain residual risk, and you would, when you visited, accept that risk knowing what it is. You would notice that the National Park Service and USGS have, in the post-2024 period, invested significantly in monitoring at one specific pool, and you would understand why. You would notice that the same logic, applied across the rest of the park, would suggest more monitoring at more features, and you would understand that the budget for that monitoring is set by Congress through the appropriations process. You would, in short, see Yellowstone the way the data shows it to be, rather than the way the imagination has built it. And when, some morning a few months from now, the webcam at Black Diamond Pool catches another event, and it almost certainly will, you would understand what you were looking at. Not as a sign of impending catastrophe, not as evidence that the supervolcano is waking, not as a footnote to the larger story of an eruption that will not, in any meaningful time frame, occur. You would see it as what it is. A small expression of the system that has been operating for hundreds of thousands of years. A reminder that the actual dangerous thing about this place is not the dramatic event in the imagination, but the modest event in the data. A pool in a basin on a clear morning exploding. The real Yellowstone threat has been erupting all along. It has been erupting for hundreds of thousands of years. It has been erupting on quiet boardwalks in front of webcams. It has been erupting at night under ice cover. It has been erupting in basins we have never closed off and in basins we have. It has been erupting on the small end of a distribution that, at the large end, has carved bays into lakes and reshaped quadrants of the park. It is what the system does. It is the part of the system we have, until very recently, looked past on our way to the part of the system we have, until very recently, almost entirely imagined. The webcam will keep watching. The sensors will keep recording. The pool will keep refilling. Somewhere in the next 12 months, a sixth event will occur, and a seventh, and an eighth. Each of them will go into the record. Each of them will be analysed. Each of them will tell us a little more about a system that, every year, every month, every Tuesday morning at 10:49, is doing exactly what it has always done, which is to say, the system is dangerous. It has always been dangerous. It is dangerous in a specific way, on a specific scale, at a specific kind of place. And the question for us, the ones doing the watching, is whether we can finally see it for what it is. Not the imagined catastrophe, the real one, the one already happening.